The purpose of this video is to demonstrate how to design pile lengths and prepare plan notes based on LRFD geotechnical design procedures using a spreadsheet developed by the Iowa DOT Office of Bridges and Structures. In particular, we will consider the H30 2006 standards, which can be found at this website address. We'll look at a 243-foot bridge length with a 0-degree skew. We'll consider the integral abutments, and we'll look at the HP 10x57 steel piling with 10 feet of pre-bore at those abutments. We'll look at structural resistance level 1 or SRL1, which we'll talk about a little more later. The generalized soil category will be cohesive soil, and we will consider setup. Construction control uses WEEP. From here, we'll jump to the H30 2006 3-span pre-tension pre-stressed concrete beam bridge standards. And we'll scroll down to page 1A and zoom in on the general notes. So as we said, we'll look at the 243-foot bridge length with a 0-degree skew. Scrolling down to note 3 here, you can see the abutment piling are to be driven through oversized holes pre-bored to a minimum of 10 feet below the bottom of the footing, and we will consider that as well. Scrolling down further, here we have the integral abutments on this first bullet with HP 10x57 piles, and we will look at structural resistance level 1, as we said. So the note here talks about structural resistance level 1 or SRL1 as being essentially equal to the ASD 50-ton steel pile designation. So the LRFD equivalent of the 50-ton ASD steel designation is SRL1. So scrolling back up, and a little too far there, sliding over to the right. Still on page 1A, this first paragraph. As you can see, it says the H30 standards were revised based on the Iowa State University research done in 2012. Of course, that's led to some changes in how pile design is handled, and also the notes that go on the plan set. Those are mentioned here and can be found in the Bridge Design Manual, and we will look at these further with the spreadsheet as well. So the plan sheets you put together will have these notes on them, and then those plan sheets will reference these H30 standards for the other portions of the bridge. And from here we're going to zoom out and head to the integral abutment sheet on page 6. We're going to zoom in, scroll down to the bottom of the page, and slide over to this table. Scroll up a little bit. So looking at this table, as we said, we're looking at the 243-foot bridge length. You can see we have 9 piles in each abutment, so 2 wing piles, 7 piles in the main cap. Now the load per pile, which is designated P sub U, or the strength 1 factor design load in kips, is 138 kips per pile. And this load would include like factored superstructure dead load, factored superstructure live load plus impact, and factored substructure dead load, as it would apply, of course, to this abutment and in particular to each pile. So we have 138 kips per pile, but as it says down here, this is not the value the contractor is interested in for driving the pile. Rather, this pile will be used by you, the designer, in order to develop the value that the contractor will be interested in order to achieve capacity. So from here, we're going to go to the bridge manual briefly. We'll look at Chapter 6, Section 2, or 6.2, the piling section. We're interested in BDM Section 6261 that deals with steel H piling. We'll click on the hyperlink, which will take us there. We'll scroll down and you'll see structural resistance level 1 mentioned here. And for our particular example, we will have this H pile that tips out in soil and will be designed for friction and end bearing in the soil. Now additionally, with this structural resistance level 1, you can see that there's a phi sub c factor, resistance factor mentioned here, of 0.6, and this structural resistance factor, phi sub c, is used in order to get the structural capacity of the pile. And you can see here it's for normal driving conditions, which would be generally typical for an SRL1, not severe driving, which has a lower phi sub c. But we'll use this value as we scroll down to this next table, table 6261-1. We have HP 10 by 57 piling, and we are in SRL level 1, so there's 243 kips of nominal structural resistance that our pile needs to be able to support or will have. So that 0.6 structural resistance factor times this nominal structural resistance of 243 kips. If you multiply those together, you get 145 kips of factored structural resistance. Now if you remember from the H30 standards, the abutment we looked at, we had 138 kips of factored load, or P sub u, so that is less than the 145 kips of factored structural resistance, or in other words the 0.6 times this 243 kips. So structurally the pile in the ground is satisfactory for this particular check. So moving on from here, I want to scroll down and show a few other things in the bridge design manual. So if you scroll down far enough, you'll get to Article 627, Nominal Geotechnical Resistance, dealing with the soil. And scroll down a little further and you'll come to the end bearing geotechnical resistance table. This has the nominal values for end bearing, and we'll look at this for our HP 10 by 57s for some end bearing in the soil that we have. If you go to the next page, you have the friction chart for the various soil layer types and the various pile types. I also just want to quickly point out these upper and lower entries in this chart. The upper entry having a lower magnitude of friction resistance. So if you are 30 feet or higher, 30 feet from the natural ground line, if you're above that 30 feet line, then you would use these upper values. If you're below that 30-foot line, you would use these lower values, and we will make use of this in our example. So just to point that out. If you keep scrolling down, you'll see there's also the soil categories. Essentially there are three. There's cohesive, mixed, and non-cohesive, and these are the generalized soil categories. And the way this is approached is the typical soil categories along the pile will either be cohesive or non-cohesive according to the classifications here, which should be in your boring information. And so as each layer is designated cohesive or non-cohesive, when you look at the full pile length and all the soil in contact with the pile, you could then figure out the percentage of cohesive and non-cohesive, and then from there make a determination as to whether the generalized soil category along the full pile length should be cohesive, mixed, or non-cohesive. And we will look at that more as we get into our example. Scrolling down a little further, we have the resistance factors in 629. We have three charts there. This is the resistance factors for design or for determining contract pile length. And we are using Weave for construction control. So we're along this line. We are going to assume we have a generalized cohesive soil category. So we are going to be using this 0.65 value for our geotechnical resistance factor. Scrolling down, we have another chart for axial tension in our pile group. We're not going to look at this in this example, so we'll bypass that one. Looking at the third table, this is for developing the target nominal or the target driving resistance for the strength limit state. And once again, we have WEEP as construction control. So we're in this row. We will assume we have a cohesive soil, and since we're considering setup, we have two factors here. We have the 0.65 for the end of drive resistance factor and the 0.2 for the setup resistance factor, which we'll make use of. Scrolling down a little further, it talks more about soil setup in cohesive soils, which in Iowa, as stated in the Bridge Design Manual, we only consider setup when you have steel piling, when you have WEEP for construction control, and when your generalized soil category is cohesive. So what we do is we use an average blow count along the pile in order to determine a setup factor, which can be done from this graph. And so on the x-axis here, using that average blow count along the pile, you can see that the setup factor increases with the blow count being less. And also there are lines for different days past the end of drive. So if you're 1 day past the end of drive, you look on one line here, one curve, and then if you're 3 days or more, you look at another curve. And generally, you want to stay out of this area in yellow, since it's not necessarily as certain as some of this other information is. Alright, so from here, we're going to move to our particular example. So we have a west abutment. We have HP 10 by 57 piling. This piece of U of 138 kips was taken from the H30 standards. Our borehole number is F1621. Presumably this is somewhere near our abutment. We have an 80-foot deep boring. And if we scroll down a little, we can start looking at the soil layers. So at 1007, we're approximately at the roadway surface, and our first layer is a layer of fill, just 3 feet thick to get down to the existing ground surface at 1004, and then that's where our boring would start, our boring information. So you can also see in this second layer we'll have the bottom of footing elevation starting at elevation 1000. And this layer 2 will be a soft silty clay, 10 feet thick, extending down to elevation 994. And the average blow count in this layer is assumed to be 3, and the nominal geotechnical resistance from the friction chart is 0.8 kips per foot. So once again, this is a clay layer or a cohesive layer that we're looking at. Now this layer itself doesn't matter too much because we have 10 feet of pre-bore from the bottom of our cap, and that's going to extend right through this layer. So essentially we're not getting any friction resistance from it. So going down to layer 3, we have a silty sand that's non-cohesive, beginning at elevation 994, extending 6 feet down to elevation 988. And you can see our pre-bore ends in this layer at elevation 990. So some of this layer will provide friction resistance over this length. So this layer has an average blow count value of 8 blows per foot, a nominal friction resistance of 1.2 kips per foot. Going down, we have layer 4, which is a firm sandy glacial clay, 14 feet thick, extending down to elevation 974. The average blow count is 13. The nominal friction resistance of this cohesive layer is 2.8 kips per foot. And here is the 30-foot mark below natural ground line at elevation 974. And so this glacial clay would be using the upper value in the friction chart since it's above the 30-foot mark. Scrolling down, we're now below the 30-foot mark, and we have a very firm sandy glacial clay, or layer 5, with an average blow count of 25 blows per foot. So we can use the lower value from the friction chart for this material, and we get a nominal friction resistance of 4 kips per foot. So this last layer is 50 foot thick down to the bottom of the boring, at elevation 924. And this material is good enough in order to have some end bearing on our HP 10 by 57 piling. So we have 16.7 inches squared cross-sectional area for this piling. We have a nominal bearing resistance of 2 KSI, so that gives a total nominal end bearing resistance of 33.4 kips on the end of our pile. So this is the example we're going to look at in the spreadsheet. And from here we will jump to the spreadsheet, looking at the description tab just briefly. It's got some general information about the spreadsheet, describes some of the other tabs, and also has the disclaimer listed there. But we'll dive in and go to the pile length tab, where we will begin entry of our particular example. And in our case, as we're just going to call this H30-06 for the 243 foot bridge length. We are looking at the west abutment. Now this first entry is not used anywhere really in the spreadsheet, it's just for information. The second entry is used in the plan notes. The third entry just designates the boring number, which we said was F1621. Once again, just for information. The natural ground line is 1004, which is essentially corresponds with our top of boring. And this is just used to establish the 30 feet below sort of mark that's over here, this 974. So 974 plus 30 feet is 1004. Now the water table is, once again, just for information. The spreadsheet does not use this value for anything, and since we didn't have one listed, we'll just delete it and leave it blank. The bottom of cap elevation was 1000. We do not have any scour at our abutment. We did want to consider pre-bore, so we enter Y for yes, and the 10 foot of pre-bore is already in the entry, so that's fine. So our bottom of boring, our boring extended down to elevation 924, and now we can scroll down to put the entry in for our particular soil layers, and this is the old data, so we'll just highlight it and delete it, and then we'll start entry with our first layer, which begins at elevation 1007, and this is just the fill layer. Now we don't need any other information entered for the fill layer because it's actually not in contact with our pile. So it's not going to provide any resistance, and we don't have any down drag, so it doesn't play in at all on this example. Layer 2 begins at elevation 1004. That layer is a soft silty clay. That's a cohesive layer. We don't have any down drag. The average blow count was 3 blows per foot. The nominal friction resistance was 0.8 kips per foot. For end bearing, you can put in values for each layer if you want to, but in general, if you kind of know where your pile tips out, you only need to put in the end bearing at that layer. And we're just going to do that on our last layer because we're pretty sure our pile is going to tip out there. So layer 3 begins at elevation 994. That was a silty sand, and that is non-cohesive. And these designations for cohesive and non-cohesive are particularly important just to help determine the generalized soil category, and then also if you do have a cohesive soil, it's used to get the average N for those layers, which is used for setup calculations. So the average N in this layer is 8 blows per foot, and the nominal friction resistance is 1.2 kips per foot. So layer 4 begins at elevation 988. It's a firm, sandy glacial clay. So that would be cohesive. The average blow count for that layer is 13. and we have 2.8 kips per foot of nominal friction resistance there. So the final layer begins at elevation 974 and extends down to the bottom of the boring, which you do not want to enter the bottom of the boring down below this. We've already got it up above. You can run into problems if you kind of cut a layer, put the bottom of boring elevation in the spreadsheet. If the pile needs to extend below that, might run into some trouble there. So this is a very firm sandy glacial clay. Once again, it's cohesive, and we have an average blow count of 25. And we're assuming 4 kips per foot of nominal friction resistance. And as we mentioned, we do have end bearing in this layer, and in particular we have 33.4 kips of nominal end bearing resistance that we calculated just a little earlier. So that is all of our data for the soil layers that we need. So scrolling down, we're going to look at our piling. We have HP 10 by 57 piling. Once again, this is just for information, as is the pile area of 16.8 inches squared. Now we are assuming we're going to have 1 foot of waste for pile cutoff, just due to damage and driving the pile. And if you hover over these little red triangles, you can get additional information to help on some of the entries and explanations. Once again, for an integral abutment, we assume we have 2 feet of a pile embedment into the cap, and we will also be rounding our pile to the nearest 5-foot increment. That's something we do for steel piling, and so that's set properly. The factored axial load per pile, this is actually the piece of U from the H30 standards, and that value was 138 kips for this example. Now, as we said, we're assuming we kind of have a cohesive soil. So if you go over to this abbreviated resistance factor chart for design, I've got the values in there for the weep construction control. And so for cohesive soil, we have a 0.65. So we put that in. It's already in there for us. We'll also use that for the end bearing, since we are figuring we're going to tip out in a cohesive soil and we're not coming down to bedrock or some other soil type. So we'll stick with the 0.65 there as well. We do not have any down drag in this example. So from here, this older data will be updated when we click the button. And we want to click this button first, which will estimate a contract pile length. So we click it, and it estimates that the pile needs to be 65 foot long in order to get capacity. So as you can see, we started, the spreadsheet took care of this. It's got the bottom of cap elevation, the pre-bore zone. We did have 10 feet of pre-bore. So there's no capacity in these first 2 rows because there's none in the pre-bore zone. And then the pre-bore extends down into layer 3, so that's kind of where we're starting to get capacity in the silty sand, which is non-cohesive. So the length over which we have capacity in that layer is 2 foot. The factored friction resistance is 0.78 kips per foot, so 2 times that gives us our total friction, factored friction resistance in that layer of 1.56 kips. And then the other 2 layers, similarly, we have our factored friction resistance, and in the last layer we also have the factored end bearing resistance of 21.71 kips. So all of these factored resistances are summed up here cumulatively for 138 kips of factored friction resistance. And if you recall, our factored load was P sub U of 138 kips. So we've matched our demand with our supply exactly, or the spreadsheet did. So we are okay in terms of pile length, and the pile length is added up from these rows. You have 60.33 feet of pile, which does not include pile embedment into the cap of 2 feet and the pile cutoff of 1 foot. But we will be adding that in here, or the spreadsheet will be. We had no factored down drag load. We did have a P sub U of 138 kips, so the total load on our pile is still 138 kips. And as we said, our factored resistance is 138 kips. So the soil in contact with the pile total is 50.33 feet. Remember, the pre-bore soil, or the soil that is being pre-bored through, is not in contact, so that's not counted here. And of that length, 48.33 feet is cohesive and 2 feet is non-cohesive. So you can see we do have cohesive, a generalized soil category of cohesive, which is listed here as C. If this were something else, we would have to go back up and perhaps change our resistance factors. But in our case, we do have a cohesive generalized soil category. So the program also rounds based on this number 1. That's the button we hit. It's going to round off this pile length of 60.33 feet plus the 1 foot of cutoff plus the 2 feet embedment in our cap, and then it rounds it to the nearest 5 feet for 65 foot of contract pile length. And here we also have the nominal design pile resistance listed, both for friction and then for end bearing, and then the total is 212.31 kips. So scrolling back up, we know that our contract length is 65 feet, so we tend to want to set that in this other entry for button number 2. You might want to put in 60, 65, or 70 feet to the nearest 5 feet, and then let the spreadsheet recalculate based on this set length. So we are going to use the 65 feet. So we'll hit the button. So everything is being updated based on that 65 feet. We get 142.35 kips of capacity, which you can see here. So you can see that went up a little from the 138 kips we had before, and that's because the pile overall was rounded up. Now you, of course, still pull out the cutoff and the 2 foot embedment into the cap, but it's still higher than it was before, because you can see this is now 62 foot of cumulative pile length, which is taken from here. And then you add in the 1 foot of cutoff and 2 foot embedment into the cap, and you get 65. So once again, you can see the factored resistance is greater than the load, so the pile is, or the soil geotechnical resistance capacity is fine. We have no warnings to consider. You can see we're still in a generalized soil category of cohesive, which we would expect. So the contract length 65 feet, the total nominal design pile resistance is 219 kips. So that sort of takes care of this upper part of the spreadsheet. And now we want to move into the lower part, which deals with the target nominal pile driving resistance in the construction stage. So the contractor is going to be interested in the values that come out of here. So some of this information is grabbed from above. It's being reused. In our case, these entries are actually fine because we are looking at a cohesive soil, we have steel pile, and we're using WEEP as construction control, so we can consider setup, and we will. So our resistance factors for end of drive are 0.65 and for setup are 0.2, and those are entered. We are not tipping out in bedrock, so this is no. So everything is already entered correctly for us. So scrolling down, we have this third button that we want to click to determine the target nominal pile driving resistance. So we'll click that. This chart is updated based on the entry above. We're just going to primarily look at what's down here. So once again, we have a cumulative pile length of 62 feet. This excludes pile cutoff and embedment in the cap. And you can see we're still cohesive even for driving the pile, because remember, we don't have scour or anything like that, which could possibly change the soil category, because when you consider driving, you typically consider you might be driving through the scourable material, but in our case we don't have any. So we're still cohesive, which means these resistance factors we used up here are good. Scrolling back down, as I said, the average N along the pile length for the cohesive soil layers is 21.6. So this is the average N blow count for all the cohesive layers that are in contact with our pile during driving. And based on this 21.6, you would go, if you remember the chart, which is reproduced here, you might come out here at 21.6, come up to this 1 day curve, where you hit the curve and then you'd come over and maybe you'd hit about 1.43 or 1.44 or something for the F setup factor. So the spreadsheet does this for you. You can see it is 1.44 for 1 day. 3 days is 1.5, and F setup for 7 days is 1.55. And how this is used is explained more in the Bridge Design Manual. We're not going to get into that here. The spreadsheet also calculates a target resistance factor, which is based on these two values of 0.65 and 0.2, and the F setup for 7 day, because this is on a 7-day basis. So that information is combined in order to give this 0.76 target resistance factor. And so that factor is used in determining the target pile driving resistance at the end of drive. So essentially what we do is we sort of, when we have setup, we lower the end of drive value because we're going to assume we're going to get setup 1 day later, 3 days later, 7 days later, and that the pile will reach capacity. And we're conservative when we do that, so we are expecting it to happen. So in this case, the contractor is interested in this end of drive value because this is what he's shooting for. Now, let's say he did not get it. If he had to do a retap, he might have to look at one of these. If he did a 1 day retap, he could potentially need to get 260 kips on that 1 day retap to make sure he gets capacity. However, the maximum value the contractor would need to get on any retap, or I should say the minimum retap resistance required, is 212.31 kips. So this value, you can see, is lower than these other three values listed here. And so essentially these three will not be used in the plan note because this one will override those. So if the contractor did not get 181.44 kips at the end of drive, he would need, if he retapped, he would need to get 212 kips on the next day, or 3 days later if he wants to wait that long. At that point, I think he would probably splice on extra pile and drive it down. But that's how this works. So down below here, our F setup factors, we use this equation along with these constants to generate those, and this is all used to generate the values that are used in plotting this graph. And this graph really is just for information, for viewing. You don't actually need to use it in the spreadsheet at all because it's all calculated for you. So from here, we've basically done everything we need to do on this tab. So we can jump to the plan notes and take a look at those. So these are the notes that will go on the plan, that you should put on the plan. So first of all, it says that the contract length of 65 feet for the west abutment piles is based on a cohesive soil classification, a total factored axial load per pile PSU of 138 kips, that's from the H30 standards, and a geotechnical resistance factor of 0.65. Now this last sentence we didn't do anything with. We didn't figure out some minimum tension force or some tension force we used for design. You can do that if that's necessary for your job. I should say maximum tension force. Second paragraph here says the nominal axial bearing resistance for construction control was determined from a cohesive soil classification and a geotechnical resistance factor of 0.76. So that 0.76, as you recall, comes from this row right here. So it's grabbing that, putting it in the note. The values up here are also grabbed from this other tab. But anyways, that's where the 0.76 comes from. Now the portion the contractor is interested in is this third paragraph. It says the required nominal axial bearing resistance for the west abutment piles is 91 tons. Once again, the 91 tons is coming from here, end of drive. Now this is in kips, so you divide it by 2 to get it into tons. So it's 91 tons at the end of drive, and then it says if retaps are necessary to achieve bearing, the required nominal axial bearing resistance is 106 tons at 1 day or later retaps. So that 106 tons comes from this value, 212 kips divided by 2. Remember, this value controlled over these because this is the most the contractor would have to get on a retap. So these values do not need to be used in the note. You can see they don't show up here. The note goes on to say the pile contract length shall be driven as per plan unless the pile has reached refusal. And then there is this sentence about embedding the pile a particular amount. We're not going to fill that in. Once again, if you need to include that, you can put a value in there, or if you do not need it, I guess you could delete the sentence. Now, the construction control was based upon a weep analysis with a bearing graph. Alright, then finally there's these 3 notes that are general in a sense. These notes will also go on the plan set, and they're just designed to help the contractor size his hammer. And we added this because right now the contractors are not going to be used to looking at these new values. Like 91 tons probably would seem awfully high to him. So we thought, well, let's put in kind of these old ASD values for the design bearing to give him some idea of where he needs to be with his hammer, and so that he can size the hammer. So the spreadsheet does not fill these out for you. You should calculate them. But in our case, for this example, we could say, well, if you remember, we had 138 kips from the H30 standards. And when you go from ASD to LRFD, we've sort of assumed that an average load factor in doing that is 1.45. So if we took that 138 kips PSU divided by that average load factor of 1.45 and further divided that by 2 kips per ton, you would come up with 47.6 tons. And you could enter that here to help the contractor size his hammer. And he's not supposed to use that to actually drive the pile. He's supposed to use the weep bearing graph provided. But you can see that 47.6 tons is close to the 50 tons, which, as we said, kind of corresponds between the ASD older method and the new SRL1 from the LRFD method. So you can kind of see that correlation. And then finally, on the graph tab, we kind of have a plot of what's going on with our soil layers and our integral abutment with the piles plotted here, and here's the pre-bore outline shown. So you scroll down through the layers, you can see the end of the pile, there's the end of the boring, and you know, if you hover over the end of these layers, you get some information about what layer it is and the elevation there, for instance 924. And that's all I wanted to cover in this video. Thank you.